Okay, welcome everyone, and thanks for being here at this second seminar or second Softies discussion organized by the Italian Soft Matter Days. My name is Francesca Serra. I'm at the University of Southern Denmark, and my role here is to introduce give a general introduction of what is going to happen in the next hour and 15 minutes. And then I will start introducing the protagonists of this event. So we will start with a Q&A question between where Roberto Cerbino will interview Cristina Marchetti. And then in the second half hour of the seminar, there will be a seminar by Vincenzo Vitelli. Then this will be followed by about 15 minutes of questions from the audience. So I will immediately get started by introducing Roberto Cerbino. Roberto is, well, he got his PhD from the University of Milan, then did a postdoc in Fribourg in Switzerland, then returned to Milan as an assistant and then an associate professor. And since 2021, he has become a professor at the University of Vienna. He's the inventor of the differential dynamic microscopy, which we all know and love. And of course, he did a lot of key research in colloidal science and rheology and non-equilibrium systems, more recently, and also in active material and in active matter. He's also recently become an associate editor of the journal Soft Matter. But most importantly, together with Manuela Zaccarelli and Stefano Buzzaccaro, he imagined and then he started and developed the Italian Soft Matter Days. So it's really a pleasure to have him as a part of this Q&A session as interviewer. So
thank you very much, Francesca. So it is my pleasure indeed to be presenting Cristina today. And I just was commenting before the beginning of the event that I found the 32 pages curriculum of Cristina, which is full of achievements and publications and results. And I tried to select the things that I thought were more important for this interview. And of course, there were many that will be missing. And I think it's important to stress that Cristina was born in Italy and she grew up in Pavia, where she also went to the university studying physics. That I think was not a common subject among the circle of Cristina's friends and college mates. And so as many of the Italian colleagues, she left Italy for the US, destination University of Florida, for a PhD thesis with Jim Duffy, entitled Fluctuations in Systems Far from Equilibrium, which would have been my dream thesis, I think, from the title. After getting a PhD, she did a first postdoc at the University of Maryland. I couldn't reconstruct from the publication, I think with Jay Dorfman. Is it correct? Oh, yeah. Okay.
And Bob Swansek. It was a postdoc with Bob Dorfman, Bob Swansek, yes.
And then she moved to Rockefeller University with Eddie Cohen, and then she moved to City College of the City University of New York with Mel Lacks. And in this time, she transitioned a little bit to solid state physics, dealing with semiconductor heterostructure and similar things, which continued to be her focus when she moved at the University of Illinois, Chicago, as a tenure track assistant professor. But the most defining step of her career has been to move to the Syracuse University in '87, where she remained for approximately 30 years, doing a lot of things, and I think also transitioning slowly to biological physics, which is the main subject of her research today. In 2018, she moved to UCSB, physics, as a distinguished professor. And I just want to mention in concluding that she is a member of the National Academy of Sciences. She was awarded the Leo Kadanoff Prize of the American Physical Society. She's a fellow of a large amount of societies, including, of course, APS. And I want to mention also a couple of fellowships, the Simmons Fellowship in Theoretical Physics and the Rothschild Mayen Sabbatical Fellowship that brought her to Institut Curie in 2007. So I think I have to stop because we want to leave a little bit of time to the interview. And I prepared some questions for you based also on the questions that arrived from the audience. And I also invite the audience, if they want, to ask questions in the chat. So don't be afraid, do it. We'll try to ask them in real time during the interview. Now, the first question I prepared for you is basically related to something that you think is a memorable moment or anecdote from your early days in science. Something that you think shaped your career. I don't know if it has to be planned or serendipitous, something that comes to your mind.
Well, thank you. First of all, thank you, Roberto, for a very nice introduction and for saying so many nice things about me. So, well, that's a tough question, but I think the one thing that really made a difference to me, well, first of all, going to the United States as a graduate student, that was really what defined my career. And I, as you said, I went to the University of Florida, and at that time, this was kind of an unusual things to do. And also, it was a place that really did not have many foreign graduate students. But I was very fortunate that my thesis advisor was a wonderful person, and I had a great relationship with him. I think that made a big difference in my career. But the thing I really wanted to mention was when I think was in maybe 89 or something like that. I've been around a long time, so sometimes it's difficult to remember the years. I went for a sabbatical at Harvard and started working with David Nelson. In those days, this was shortly after the discovery of ITC superconductivity. And there was a lot of interest, not just in understanding the microscopic mechanism for superconductivity in these materials, but in the fact that these were typically type 2 materials. And so the magnetic field penetrates in the form of magnetic flux lines, which, however, did not form the Abrikosov lattice, this order lattice that is typical of low temperature type 2 superconductors. And so I was, through David, introduced to the statistical physics of vortex lines in superconductors, on which I worked for quite a long time. And I think that the environment at Harvard and the close interaction with David and this particular topic, which involved non-equilibrium, quench disorder, statistical physics of complex objects, extended systems, combined with my background, which was actually in kinetic theory, and as you said, some solid state physics, really helped me kind of I felt I actually brought something new and different to the field that helped me make some advances that people kind of appreciated. And I want to mention one more thing. Sorry for going on so long. And that was a second moment in my life that I think made a big difference, which I think was around 2002, when I was at KITP for a couple of weeks for a program, but I went to a talk by Tanny Liverpool on modeling of cytoskeletal filaments in cells. And this was not the program I was attending. But again, that was to me very interesting because I saw also a relationship between, maybe stranger to you, the cytoskeletal filaments and the vortex lines. And that's when my switch to active matter and then biological physics to some extent started. So what I'm trying to say is that every time there was some interaction with somebody that kind of led to new direction in my science, that really was important, I think, in my career.
Oh, very interesting.
I don't know whether that answers your question, but
yeah. But actually, it made me come to my mind some other questions. So, how much of this was planned, and how much of this was serendipitous?
Well, going to live only to Harvard was, of course, planned, but the starting to work on vortex lines to superconductors or later on cytoskeletal filaments, none of this was planned. It was really more through discussions, interaction with people, and in the case of KITP in 2002, listening to a talk, that I became something kind of piqued my interest, and then I started reading, I started talking to people, and usually moved in that direction. Not that I suddenly abandoned everything I was doing. I started working a completely new field, but slowly I moved in new directions. Okay. So neither was really planned, I would say.
And the second question that was stimulated by your answer is about the timing. So if I remember correctly, you said 89, which is a couple of years after you moved to Syracuse. Yes. So how important do you think it was at the beginning of your tenure, more or less at the beginning of your tenure in Syracuse, to have this experience in a different place?
I think it was very important because honestly, the reason I moved to Syracuse is because they offered tenure-track jobs to both myself and my husband. And at that time, there was nobody in Syracuse working in condensed matter theory, soft or hard. So I was really quite isolated. And one of the things we negotiated actually when we moved there was a very early semester away. And so, this turned out to be very important to me in particular, because at Syracuse really I was by myself. And, at that time, nowadays, well, okay, we've all learned to interact via Zoom and so on, but this was a long time ago and things were really quite different.
Okay, so in your opinion, who are the scientists, mentors, or the figures that include, of course, both men and women? Or maybe if you don't want to refer to people, maybe some books or some articles or some, you already discussed about particular events, so I would rule this out maybe, that have played a significant role for your research on active matter. So now, if you think about active matter, which is your more recent...
On active matter specifically, I mean, I would say, as I said, Tenny Liverpool was a very young person at that time, but he's the one who motivated my move to active matter. And I interacted with Tenny very closely for a number of years. He visited me in Syracuse for extended periods. He didn't like it very much because he always came in winter and he felt it was a bit too cold, but he kept doing it anyway. So that was really, and his background was more in polymer physics, quite different from mine. And so I think that synergy was really very useful. Over the years, the person with whom I think I benefited a lot, interactions with Sriram Ramaswamy, even though we haven't really published together all that much. And there are a number including some of his early review articles. You mentioned review articles. Actually, there's a very short review article he has written for annual reviews, which I think is very nice and that I ask all my students to read. And when I was at Curie, I interacted closely with both Jean-François Joanny and Jacques Pro. Again, I think we wrote one article together before writing the long review, but somehow we had, very frequent discussions. So these were really very important interactions that actually get me to switch a little bit more. I don't really do biological physics. I do work on biologically motivated problems, but it was that time at Curie that got me more into that direction. And, I mentioned a few people, there are many others.
Yeah, sure.
I could mention. I have had also the fortune to get to know fairly well a number of women, kind of more of my generation. And that has been very nice, even though I might not have worked closely with them on science specifically, but I certainly discussed science, and there's been a very rewarding experience, because especially as a woman, when you get a little bit older, there tends to be fewer and fewer peers. And so it's nice to have at least a few.
I can understand. So these were, let's say, positive and ideal conditions, moment of optimism and productivity and excitement. But as anyone, I guess that you have faced difficulties, both scientifically and personally. So this question combines, if you want, two questions, if you allow me. The first one is, if you ever encountered a scientific problem that you said, damn, it's too hard, I want to give up, and I don't want to work on this anymore. And second, if you had a similar experience, not before because of a scientific problem, but before of boundary conditions, that you didn't feel welcome or you didn't feel comfortable where you were.
Well, when I went as a postdoc at the University of Maryland, I was working on essentially kinetic theory of plasma, something I had not really worked on before. And this involved still have a very big ring binder filled with pages and pages of calculations, equations that spill over from one page to the next, a single equation. and I was, at that time, I did feel quite discouraged because I didn't quite see where that was going. All this, a lot of calculations, somewhat tedious, not necessarily always that hard, but very hard to see what you were getting out of them. And so at that time, I was quite discouraged. And then actually I should say, when I first went to the University of Florida, honestly, I went with a Fulbright travel grant, and the Fulbright pays your travel one way, and they will not pay the return ticket for at least 1 year. If they had paid the return ticket within a month, I think my life would have been very different because I would have probably gone back. And the main reason was that I didn't feel welcomed by the other students. It was a very environment. They were all male. They were, it was a very conservative place, Florida at that time. And I was different. I was a woman. I came from Italy, and my English was not that good. And so that was very hard. Eventually, once I started making friends and got used to the environment, honestly, I actually loved it. I loved my time in Florida. Also because one of the reasons I went to the US is that once I got my laurea in Italy, I really felt very strongly I needed to be financially independent. And in the US, you get paid as a graduate student, which maybe not a lot, but allowed me to feel financially independent. And I both loved the environment eventually and loved the life I had there as a graduate student. But the beginning was very hard.
It was very hard. And as I understand, it was mainly because you were a woman coming from another country.
Yes, I think so. I was, yeah.
Do you think it's still like that?
No, it's very different. I visited the University of Florida a few months ago. I invited me to visit, and it's very different. Even the town has changed, has become much more cosmopolitan. The department has transformed itself. The graduate student body is very different. It's very different. But at that time, it was, this was a long time ago.
Yeah.
So it was the early 80s.
So at some point, I guess that there was a moment where you understood that you could make it, despite difficulties, despite everything, that you were motivated and let's say willing to and see. So we're seeing at the horizon that you could become a faculty in the US. Do you remember this moment, or it was more of a gradual process?
I don't think that there was ever a moment when I necessarily felt that way. As you mentioned in your introduction, I went through several postdocs, and partly because after I had met my husband, who is also a physicist, we were kind of trying to be, if not in the same city, at least not too far. And so I also switched topics quite a bit. At City College, you mentioned I worked on semiconductor heterostructures, and I kept working on that for a while. So which, in switching topics, I mean, I like it. I think it's a great thing, but it can make it hard to establish a reputation in a given field. And so, I just, I don't know, I just always felt that I was kind of happy with what I was doing, in spite of the fact that I stayed in Maryland. I had a bit of a hard time, sure, but there are always ups and downs in one's research. But overall, I was quite happy with what I was doing, and I especially enjoyed when I became a faculty, interacting with students and so on. And so, no, I don't think there was a moment where I said, oh yes, now I'm going to get, it just kind of, I did try to get the job in Italy at some point, but that didn't work out, clearly.
But maybe retrospectively, it was not such a bad thing.
I don't know.
Things went well.
Italy is a great place.
Yes.
And honestly, it's a little bit sad to see that of the 5 people on this screen, there are 4 Italians, and they're all outside of Italy.
Yeah.
I mean, 4 of the Italians are outside of Italy. So.
Yeah, but I mean, so what I was meaning with my comment is basically that things went well in any case, even if you remained in the US. So.
Yes, no, I have no regrets, but it's just that it was, I'm not sure how much things have changed, but it was certainly not easy when I finished university to get a position in Italy, and it remained so for a very long time.
Yeah.
Probably still is. I mean, I know it still is, actually.
So you mentioned in your previous answer that this double body, two-body problem or two-body, let's say, boundary conditions played a major role somehow in deciding destinations and setting the personal life. So maybe on a more general level, how difficult was for you in general? If I remember correctly, you have 2 daughters. How difficult has been for you in general, and still is, to balance professional life and personal life?
Well, when my husband and I got a PhD year before my husband. He was at that time doing energy physics, and he got his PhD from Caltech. And at that time, we applied for postdocs broadly, and we felt, well, as postdocs, we can be far away. And we were not even completely sure we were really going to stay together, honestly. And then eventually, at some point, you decide, well, if you want to have a life together, you also better try to be geographically relatively close. And so that's when I actually tried to get, so at some point he was at Yale, so I tried to get jobs. I went to New York City, Rockefeller, and then City College. They were closer to where he was. So yes, there were some boundary conditions, but it was fine. And then I did move from University of Illinois Chicago to Syracuse. The main motivation, actually, the real motivation was that they offered tenure-track jobs to both of us. So, and I knew there was nobody in my area in Syracuse, but I felt I could still work by myself, and then I could actually try to push the department in a new direction. And I did manage there to build quite a good group in soft matter and biological physics, which keeps growing. Has kept growing since I left, which is wonderful to see. Having children, I had my first child at the end of my first year at Syracuse, and my second one after tenure. I think it was equally hard, honestly. I don't think it makes a big difference. And at that time, we didn't really, in the US, there was no parental leave or anything, so it wasn't easy. And we kind of scrambled, between daycare, babysitters, occasionally the grandmother for a little while from New Zealand or from Italy. And it was complicated, but, in retrospect, it was a fun time. And I think things turned out pretty well, although you really would have to ask my children to really, see where they would agree.
And okay, so moving.
But yes, it was difficult, and there were times when it was challenging, especially because as anybody who has had young children knows, when they're young and they go to daycare, not only they are sick all the time, you are sick all the time. So
I know
So
something about it.
Yeah, but I had many supportive colleagues, and I had help from a lot of people.
So if we move more back to science, after your experience in active matter and biologically inspired physics, as you called it before, what do you think are the fundamental results that we achieved so far, or one or two fundamental results, and what are the challenges ahead?
Well, I think, first of all, antimatter has been a field that I think one of the great thing about this is that it has really inspired interest in a lot of people, including a lot of students, especially in the US in particular. You know, soft matter or non-equilibrium statistical physics or even biological physics has not traditionally been really highly a field that really belonged in some sense in physics departments, with a few exceptions. At University of Chicago, where Vincenzo is an exception. And a lot, for instance, here in Santa Barbara, we have a large number of undergraduates wanting to do research. But until some years ago, you know, they all want to do research in cosmology, in particle physics, and so on. And now, I think thanks to antimatter, they have learned about this field and they find it fascinating. So I think that is actually an important accomplishment. From a more scientific point of view, I think you can cite examples in which antimatter is starting or has started to really influence biology. For instance, in the understanding of morphogenesis, how the structure, for instance, of myosin in developing embryos directly correlates and determines cellular flows that eventually lead to the formation of shape of organs and organisms. For instance, all these recent works on topological defects in so-called active liquid crystals, you know, originally seemed truly just curiosity-driven, I will say, enterprise. But now people working on biology are paying attention, and there have been a number of experiments pointing to the possibility that correlating topological defects with biological processor or biological functions. So I think it is an area, and it has really led to a lot of advances and interest in general in non-equilibrium science, I would say, which is clearly important since most of the world is out of equilibrium after all. So, and then you were asking me something else, I kind of forgot.
No, I mean the challenges ahead.
Yes, so the field is becoming very mature, clearly, okay? And I think the interest is shifting a little bit more towards questions such as for instance, in biology, there will be question about metabolism, what is the energy needed for a particular biological functions, and correspondingly in antimatter, people are really interested in understanding energy consumption, what it needs to drive and maintain a system out of equilibrium, and so on. Another, I think, fairly open direction is really trying to start thinking about antimatter systems that are no longer dead, let's say, in the sense that like living systems are capable of sensing their environment, adapt to it. So we need to incorporate internal degrees of freedom in our so-called active particles and have them and learn how to control their behavior and how to have these particles able to respond to localized control and adapt their behavior. And I think this is becoming possible through, you know, controlled experiments in this area becoming possible through optogenetically modified protein, for instance. And I know Vincenzo is actually doing quite a bit of work in this direction, for instance.
So
maybe our time is up because yes. I see Vincenzo coming back.
Yes. My internal degrees of freedom, and I'm sure of all the attendees are very excited. Thank you very much for your time and for this very nice discussion. And
thank you, Roberto and Francesca. And I look forward to hear Vincenzo's talk now.
Thank you very much to Cristina and to Roberto for the wonderful discussion. Really very interesting also for me personally on active matter and liquid crystal. But now I have to keep the time. And so it is really my pleasure to introduce the seminar speaker, that is Vincenzo Vitelli. Vincenzo did his PhD at Harvard University, and then he was a postdoc at the University of Pennsylvania. Then he spent he got several fellowships to spend time at the Weizmann Institute and also at the SPCI and École Normale in Paris. He became a professor in Leiden, I believe in 2015, where he was the chair of condensed matter theory. But since 2017, he's been the professor of the physics department at the University of Chicago. Vincenzo received several prizes, including the Callan Prize, and he became a fellow of the American Physical Society, one of the GSOFT fellows, for his theoretical contribution on topological mechanics. But really, Vincenzo has worked on so many different areas of soft matter, and he will, I guess he will tell about some of that. But also he always looked beyond soft matter and in a lot of analogies between soft and hard condensed matter systems. So really his work is positioned at in between biophysics and physics and math, engineering, robotics. So he's really polymath type of scientist. And another characteristic, which I think is always the case for all of Vincenzo's work, is that he's done a lot of collaboration also with experimentalists. And so all his work is also really rooted in interesting experiments and in try to understand or inspiring future experiments. So I'm very excited to hear what he will be talking about. And please.
Hi, everybody. Thank you, Francesca, for this very kind introduction. Let me get started here. Please, can I ask you, Francesca, if you can see my screen? Perfect.
Yes, I can see your screen.
Okay. So the title of this presentation is All the Turbulence, How Patterns Emerge from Arrested Cascades. And I will tell you what the meaning of all those words is during the course of this talk. First of all, I would like to say that this is work done in collaboration with Xander de Witt, who is a PhD student at in Twente. Michel Frouchard, who was a postdoc here in Chicago, is now a faculty in Paris in the SPCI. Tali Hein, who is a PhD student in my group, and my friend and longtime collaborator, Federico Toschi. And you can read a version of this on the archive, and hopefully it will be shortly published. So I would like to start by telling you a little bit about pattern formation and a little bit about turbulence and why we're thinking about the two of them together. Turbulence is usually not associated with patterns or any ordered structure. So this may be at first sight a strange association. So let me just start with what do people typically associate with pattern formation. And with a touch of humor, let me introduce you my cat, Lauro, here on the right. Hopefully you can see him sporting a rather elegant pattern on himself, and it's a pattern of spots. And for a long time, people have been interested in trying to understand pattern formation from cosmological scales to even biophysics. Think about Turing, for example, and often feline of various types, like leopards and cats, have been used as metaphors for this process. Now, this is not going to be a talk about cats, but nonetheless, any problem of pattern formation is usually characterized by a length scale of an inverse wave vector, what I call here kc to the -1, that characterizes the size of that pattern, the spacing, for example, of spot, the sizes of layer. And so the first question in pattern formation is, what selects that length scale, okay? And in its simplest incarnation, at the textbook level, usually what you assume is that at the beginning, there is an homogeneous state. And then at some point, you perform what people would call a linear stability analysis. You ask whether modes of a given wave vector, k, are stable or unstable by looking at their growth rate that is denoted here as sigma k. Within this linear stability analysis, you can single out which mode grows the fastest, and say you can denote it by kc. And the linear stability analysis perspective on pattern formation is that this mode will then grow. And as it grows, of course, nonlinearity plays an important role and will eventually determine what the actual pattern will be. But the mechanism of wavelength selection is essentially coming from a linear stability analysis around an homogeneous state. Okay? So this is a very common mechanism. There's several instantiations of it. It is also the advantage of being simple to describe, and hence it's a favorite of textbook. But this is by no means the only possibility. And somehow we will operate in this talk in the opposite extreme. We're going to go to an extreme in which the background, the generated pattern, is not homogeneous, but is actually a turbulent state to start with. And even if you don't know anything about turbulence yet, you may not associate it with homogeneity, with a uniform structureless state. I mean, it's something, you know, at least it's a chaotic state. And the second thing is that the mechanism that selects the wavelength will be strongly nonlinear. Okay, so in the spirit of joining these two worlds, the world of pattern formation, the world of turbulence, I would like to introduce to you, I apologize for those who are already experts in the subject, the notion of a turbulent cascade, okay? Exemplified by this power spectrum for the velocity field. I'll explain this in detail. The only thing I want to tell you first, before even going into the technical details, is that a beautiful argument and powerful and correct was developed for the power law that this spectrum exhibit by Nikolai Kolmogorov. It was a true achievement, and there is a quote that I find very inspiring by Kolmogorov. Kolmogorov says that there's a fine layer between the trivial and the impossible, and mathematical discoveries are made in this layer. And perhaps the determination of this exponent for this power law by Kolmogorov, which is a very simple and beautiful argument that we'll review later, is one such achievement. But before even going into details of what is this direct cascade, I just want to stress the picture that you should have in your mind when you think about turbulence is a maze of vortices bent in all sorts of directions, like a tangle of disordered spaghetti. Once you cook them, so that they can bend a lot. And at the same time, what I'm telling you is that there is a power law in K space, and power laws do not have a favorite K. They're by definition defining, structureless processes that do not select a wavelength. So it seems a little bit strange to even put together pattern formation, whose essence is wavelength selection, with something that exhibits a power law in K. So I would like to explain this connection during this course, but let me first start by telling you a little bit about this graph that you see on the left. First of all, what is that we are doing there? So before doing that, I want to introduce you, at least those who are not familiar with hydrodynamics, with the concept of a Reynolds number. And I would like to start by first writing down the so-called Navier-Stokes equations. Now, Navier-Stokes equations are the pillar on which the description of simple fluid is built upon. And so in this equation that you see written here, there is a velocity field V. And on the left-hand side, please forget for a moment this RE. Here is a derivative of the velocity field. So this is, if you like, acceleration. And this is a convective term. And then on the right-hand side, there's gradient of pressure, and there is Laplacian of velocity. This term is associated with viscosity normally. Now, this Navier-Stokes equation has been written by me here in a dimensionless form. meaning that we have redefined the V, that's why there is a tilde, or the T, that's why there is a tilde, in such a way that we're going to use dimensionless unit. When we do that, we can see that the left-hand side of this equation is multiplied by a number called a Reynolds number. This number is given by the characteristic velocity scale, the typical size of structures that produce the turbulence. For example, if you have a ball and there's a flow past the ball will have a radius, and you can put here the characteristic size. And then eta is the viscosity. Okay, so this is a number, depending that controls essentially the type of flow that you will obtain. Now, the regime that we're going to call turbulent happens when this Reynolds number is much larger than 1. Notice this can be achieved in many ways. You can go to very high velocity. You could also have to go to very small viscosities. Okay, but the aspect I'd like to draw your attention to is that since the Reynolds number multiplies the left-hand side of this equation, then when the Reynolds number is much larger than 1, the right-hand side of the equation can be neglected. Okay, and the right-hand side of the equation is associated with dissipation. Okay, the left-hand side of the equation does not. And so the key insight of Kolmogorov was the following. When the Reynolds number is large, structure like vortices can split, or he likes to use the word eddies, represented here. So imagine that you inject energy at a very large scale by steering a big box. You can form eddies, but if the Reynolds number is large, these eddies cannot dissipate energy. The only thing they can do is they can split or into smaller and smaller eddies. And if you plot the power spectrum, defined as I do here in this equation, as a function of k, you can imagine that there is a cascade of energy that goes from the large eddies to the smaller and smaller eddies. And this cascade stops when the eddies reach a size such that you put it in this equation and you get again Reynolds number order 1. In between, there is a power law distribution with respect to k, or the power spectrum. And Kolmogorov was able to use essentially some refined version of this reasoning to even figure out that the power law was -5/3. Quite an achievement. Okay. Now, for the purpose of this talk, again, the only thing you have to take is that there is a flux of energy from small k, which means large length scale, think of large eddies, to small k's. And in between, just the structureless power law distribution. This is what people call the direct cascade in turbulence. Okay. Now, at first sight, this seems eminently useless for our purposes of finding wavelength selection, because, as I said, in this power law, there isn't a k that is being singled out. The only two things, the only k's that exist are the largest k and the smallest k, which are inherently associated with the, say, the system size, the smallest k, and the largest one with the dissipative scale. But there's no structure in between. What we would like is to create one structure in between so that we can associate it, at least potentially, with the formation of patterns. Now, I would like to introduce to a variant of this notion of the direct cascade. Itself quite an achievement that took many years to figure out, which is the notion of an inverse cascade. This inverse cascade occurs in various contexts, most notably in two-dimensional systems. In that sense, it's also quite relevant to active matter, although many active matter systems are not inertial, like the equation that I showed. They are overdamped, whereas, as you notice, the equation that I'm considering here are definitely underdamped. Nonetheless, in two-dimensional system, and also in rotating turbulence. Rotating turbulence means when you take a box of fluid and you rotate it while simultaneously going to high Reynolds number. This experiment is literally performed at any instance of time in our atmosphere, for example. But if you have these conditions, you have an inverse cascade, which means that the energy is flowing from high k to small k, which means it goes from small structure to large structure. Exactly the opposite of what I described before, hence the name inverse cascade. And the final state is essentially two, if you work with periodic boundary condition in a box, is two vortices, a large of opposite sign, corresponding to the largest scale to which the energy flows. But the point that I want to draw your attention again is that while the flux is the opposite way as in a direct cascade, it's still a power law. And the power law by itself doesn't have, again, except for the larger scale and the smaller scale, an intermediate length scale being selected. Okay? So this also is not going to work in order to reproduce a mechanism of pattern selection like I want here in the pattern formation. Okay? So our idea was to try to consider a mixed cascade, a cascade that combines both a direct and a inverse one. And I'm going to first sketch the idea in its generality, perhaps a bit abstract, and then I will give you an example how you could potentially realize such things, maybe even in experiments eventually, and some speculation on where in nature you could find this phenomena as well. So here is our notion of a mixed cascade. What we're thinking is the following. Imagine that you could combine a direct cascade that operates as small k, that is to say a large length, that gets and an inverse cascade that operates when the wave vector is very large or the length scales are small. If you could interact that inverse cascade and the direct one as some intermediate wave vector, then you could imagine the energy being focused at that value of kc, and you could then make structures or patterns characterized by the length scale associated with inverse wave vector kc, where these two cascades meet and are arrested. And notice that for this picture to be effective, to work, you need both the arrest of these two cascades, but also the fact that the energy must point inwards. The fluxes must point inwards so that you condense the energy at that chosen wave vector. When that happens, you could imagine forming a vortex structure like the one I described, and their spacing, for example, could be given by kc to the -1. Okay. Now, when you view this, you say, okay, well, that would be wonderful, this pattern formation by the dissipative arrest of inverse cascade, if you could do it. But I mean, you know, where is the evidence that such a thing could even exist in nature, even in principle? And so this is what I would like to introduce you to a third variant of turbulence, which is what we focused on, that I like to call odd turbulence. It is admittedly a little bit bizarre, but the name odd also follows from technical reason that I would like to highlight. So let me get back to Navier-Stokes equation, and let me provide an introduction to this concept of odd viscosity that in various communities also known as Hall viscosity, primarily in literature, in quantum literature, or gyro viscosity, which is a name that is used in the plasma community. And this is, again, a concept that we did not invent. I think especially in the plasma community, you can see hints of this phenomena even in Landau-Lifshitz described. So, but let me tell you what it is, okay? So this is Navier-Stokes equation, rewritten in an even more perhaps intimidating form, with all the gory details of indices, but fundamentally is the same thing. Here is the derivative of the velocity, where I've absorbed also the convective term, where the nonlinearities are, gradient of pressure, some force that forces the fluid, like the steering that I was describing. And here is the viscous term. Notice that there are two derivatives operating on the velocity field. And then there is this tensor, okay? So, you know, the viscosity coefficient doesn't have to be just a coefficient. You know, if you have an anisotropic medium or a complex medium, it may have many components, for example, in liquid crystals, right? But there are some constraints that this object typically has that comes from it being associated with energy dissipation. In particular, if you want viscosity to be a viscous term, to be associated with dissipation, then the viscosity tensor should be symmetric under exchange of pairs of indices, like ij and kl. Should, you know, this object should be symmetric. if this object is not symmetric as indicated by this equation under exchange of parallel indices, for example, if it has an odd part, that's to say a part that picks up a minus sign when you flip these two indices, then all of a sudden that component will not be coming out from energy dissipation. In other words, a node viscosity does not dissipate. Nonetheless, you can still write it in the equation of motion. One way of thinking about it is in the simplest form. Navier-Stokes equation is a conservation law for momentum, okay? And this is a way of writing Navier-Stokes equation with a shear viscosity that is called mu, that you're all familiar with. And the odd viscosity in this matrix representation would be a Laplacian, would be an off-diagonal term, but with a minus sign in front. So such a term would not be allowed in a simple fluid, but it is allowed if you have, for example, fluid made of self-spinning particles or plasma in magnetic field, like a charged particle in the magnetic fields, okay? And if you want to know a little bit more about this topic, you can consult this, this review paper that we've recently written. Two aspects that I want to draw to your attention is this odd viscosity, both from the mathematical form you see here. Notice that being off diagonal, this term essentially is multiplying an antisymmetric matrix, which is associated with rotation. And even if you look at the physical origin that I invoked, either magnetic field or particles that are self-spinning, these objects have a chirality. So allowing for an odd viscosity term in the Navier-Stokes equation means probing the effect of chirality on this fluid, okay? And we would like to do that precisely in the turbulent regime. Now, I cannot resist mentioning that, even if it's not going to be perhaps as relevant for this talk, that in addition to the odd viscosity that is not associated with energy dissipation, there is also an object called odd, there's also an idea called odd elasticity, which means that the elastic tensor, which is the relation between stress and strain rather than stress and strain rate, can also display can also be non-symmetric. When that happens, it means that you're describing mechanics in the absence of an elastic potential. So this odd world, strange as it may seem, does exist in reality, both in terms of the odd viscosity and the odd elasticity. And before reviewing the effect on turbulence, I would like to give you a couple of examples of instances in practice where the odd viscosity has been measured or it exists across various domains of science. Okay? In leaving these introductory slides, let's just keep in mind two facts. Odd viscosity will give you chirality and also is inherently non-dissipative because it comes precisely from the antisymmetric part of the tensor that is not associated with dissipation. However, it does enter the equation of motion in a very similar way to the shear viscosity. Okay? So where is odd viscosity been seen? Well, let me start from some more recent experiments. This one over here on the bottom left it's been done here at Chicago by William Irwin. What William did is he took a bunch of spinning colloids, let's to say colloids with an in-plane magnetic dipole, and then he puts an in-plane magnetic field and he rotates the magnetic field. As a result of that, the colloids themselves spin, and they can make fluids or solids. And William has measured the odd viscosity in these systems. Another system that is a little bit different, but has something similar in spirit to the one I just described, is spinning embryos. This has been studied by various people, but I would like to draw your attention in particular to this work by the Fakhri group in MIT. What Nikta and company did, they took these embryos, they naturally spin, and they studied the crystals and the fluids that are made by an ensemble of them, a large number of them, large as you can see in the movies. And these systems will display odd elasticity in the solid and odd viscosity in the fluid. There are other examples like Dance's Volvox that have been studied, although measurements of odd viscosity or odd elasticity, to the best of my knowledge, has not been done. Rotating bacteria, but they will display this phenomena for the same reason. one place where odd viscosity has been measured a long time ago in the 70s, in Leiden, actually, where I was a faculty, in 3 dimensions. All these other systems are 2D. It's this system of polyatomic gases studied by the group of Jan Beinacker, who in 3 dimensions measured at least 2 viscosity coefficients, as shown in this plot. More recently, odd viscosity was measured in graphene by Andre Geim. There's this nice science paper very recently. And there's speculation that also neuroprogenitor cell will support this mechanism. I would like to give you just a hint of where this odd viscosity emerges from microscopic consideration, or what people call kinetic theory. So imagine for a moment that you have 2 particles that are hitting each other head-on. If these were normal particles and you hit them head-on, they will just recoil along the same direction of approach. But if there was something like a friction between these 2 particles, maybe because they're spinning, and this friction could be caused, for example, by the fact that as they're spinning, they move a layer of water around them, something called the lubrication force, then the collision will give rise to a recoil at an angle, right? And that angle is caused by the fact that there may be transverse force that are due to this frictional forces or to a lubricated force of the displaced fluid around it. Now, this interaction, the lubrication forces exist, they can be calculated hydrodynamically. Similarly, friction does. If you do the calculation of taking a gas of such particle with transverse interaction, you will find that the collision violates parity. Again, there's a chirality, and that chirality at the microscopic level of the collision is inherited all the way to the fluid. Okay? Now, this is one of the microscopic mechanisms that leads to odd viscosity in fluid or self-spinning particles. Okay? Now, so odd viscosity will give you chirality and non-dissipation, and is non-dissipative. Now, let's return a little bit to turbulence. To understand the effect of odd viscosity, it's first interesting to study a similar system, which is a fluid in a rotating box. So this is a simple fluid by a rotating box. If you want to understand this system, what you have to do is you take Navier-Stokes equation and you add the term in it, which is a Coriolis force. Okay? This is a much more well-studied problem, and I really recommend this review by Alexakis and Luca Biferale that was really quite helpful to us. Now, what happens in this rotating fluid? Okay, what happens in this rotating fluid is that by virtue of the rotation, the vortex line gets straightened up, if you like, and the flow becomes quasi-2-dimensional, as shown here in this picture. And the output of the inverse cascade, in the end, if you work, for example, with periodic boundary condition simulations, as Luca and Alexakis did, you will find just 2 vortices with a positive and a negative chirality. Okay, that's what forms. And if you can understand a little bit how this 2-dimensionalization of the fluid happens using an intuitive argument I'll review momentarily. But what we are really interested in is to understand not a box, not a fluid filling a box that rotates. What we're interested in is in a fixed box by having particles in it that spin along a given axis. You see, we're putting the drive at the microscopic level of the particles. Okay, what's the difference between the two?
Sorry, I'll just warn you that it's about 5 minutes.
Okay, thank you. So the difference is that instead of adding in the Navier-Stokes equation this force term, I have to add a term which is what I wrote before, the odd viscosity times a cross product of the direction in which the magnetic field is pointing, or the rotation of the particle is pointing, times the Laplacian of V. The difference between these 2 terms is that this one is a Laplacian, and this one does not. Okay. Other than that, the mathematical structure is the same, with the odd viscosity playing the same role as a rotation field. Okay, so if you Fourier transform a Laplacian, this expression, you'll get exactly the same thing as the Coriolis force, except the Fourier transforming a Laplacian brings a factor of k squared in front, wave vector squared. So the odd viscosity acts as a wave number dependent Coriolis force. Okay, so it's like a Coriolis force that is strong a large k and disappears a small k. Now, this has some consequences that I want to review for you. If you are a small k, this effect will disappear. So you're going to have a direct cascade, as shown here. This is exactly the Kolmogorov mechanism. But if you go at very high k, then this term is very, very important and will play the same role as a rotation. That is to say, it will trigger an inverse cascade. And this is what you see here. So that's why the odd viscosity creates a mixed cascade, because it operates only selectively a large k. In between, and at a small k, it vanishes, giving rise to the normal 3D cascade. So now we have the essence of our findings. A fluid with an odd viscous term will have a mixed cascade, and the place where this mixed cascade stops is set in a way that we have to determine by the amplitude of the odd viscosity term. The odd viscosity can stop the cascade because it's a viscous term, but being not associated with dissipation is a non-dissipative mechanism of arrest of the cascade, which is a bit of an unusual thing from the perspective of Kolmogorov theory. Okay. Now, what we would like to do is to say, okay, this is a qualitative picture, but you may want to know, okay, you said that the odd viscosity sets this Kc, but how? How does Kc depend on the odd viscosity? And so the way to do that is essentially to study. We can do it in two ways, even by large-scale simulation. This is the approach that Federico and Xander have taken, or analytically, and I'll show you both. So first of all, this is what Federico and Xander did. So on the left, there is a normal fluid. By normal, in this case, I just mean a turbulent fluid, very high Reynolds number, but zero odd viscosity. And you can see the sort of characteristic disordered patterns of vortices. Here, I'm plotting the vorticity as a column map. On the right-hand side, there is a fluid with a large odd viscosity. And I would like to point out to you that perhaps even by eye, from a casual look, you can see that these two pictures are different. The one on the right shows some beginning of stripes, if you like, oriented in the z direction, the direction being singled out by the direction of spinning of the particles. And there is even a characteristic wavelength that seems to emerge even by eye. Of course, you don't want to do things by eye. You want to take a Fourier transform of the signal and see whether there is a peak. And that's exactly what the power spectrum is. And this is what Federico Xander did. And as you can see, we can plot that power spectrum that exhibit a maximum. And we can track, it's a broad maximum, which shows why this pattern is not so sharp. These are also finite size simulation, obviously. But the crucial thing I want to draw your attention, if I track the peak of this curve, as a function of odd viscosity, these curves are done with different value of odd viscosity, I can then extract numerically how the Kc, which is associated with these patterns, depends on odd viscosity. And there is this interesting power law dependence that I showed here. Now, to extract it analytically, and perhaps in the process also understand it a bit better, we're going to do a following argument. I would like to argue that this point where the two cascades meet, it's a little bit the place where eddy turbulence and wave turbulence meet together. And let me explain what I mean by that. And this is the very final slide. So you can derive the Kolmogorov spectrum from dimensional analysis using a formula due to Kreisman. And in this formula, essentially, you only need to input a characteristic time scale. If you put as a characteristic time scale what is known as the eddy turnover time, which is a characteristic time scale for a vortex to break, essentially, then you obtain the power law scaling of Kolmogorov, which is this k to the power of minus 5/3. Never mind if you don't get all the details, but the input is this time scale that is the eddy turnover time. Now, once the odd viscosity is switched on, there's a new characteristic of waves, new type of waves that are created by the odd viscosity. So what you can do, and they have a spectrum. The spectrum is omega proportional to k squared times the odd viscosity. You can calculate that directly from Navier-Stokes equation. So if you take the Kreisman formula, and instead of the characteristic time scale of the eddy turnover time, you put the frequencies of these odd waves, then you get a new power spectrum that is not Kolmogorov, but is a power spectrum characteristic of the odd turbulent system. And if you match this power spectrum with the Kolmogorov one, at Kc, you can find precisely the scaling that, that Xander and Federico derived numerically. So if you like, at small k, it's Kolmogorov scaling, dominated by the fragmentation of eddies. On the right-hand side, there is a scaling of the power spectrum that is controlled by the interaction between these odd waves generated by the odd viscosity. Okay? And in between, the patterns emerge. Now, this mechanism of arrested cascade is not restricted only to fluid made of spinning particles. We have searched for analog of it in various contexts: geophysical flows, MHD turbulence, this is plasma. And what I would like to also advertise, and this is the very final picture in our paper, is that you can also play a similar game with mass. Instead of considering cascades of energy, where is vortex that are splitting and merging, you could consider cascades of mass. In this case, there are objects that are splitting and merging. And this process can also induce wavelength selection. And this could be an interesting thing to look in a variety of contexts, from rain formation to active mixture. And with that, let me thank you again for your attention and take any question that you may have. Thank you.
Thank you very much, Vincenzo. This was very fascinating. We have about a bit less than 10 minutes for questions. So I would encourage the audience to raise a hand. I already see a raised hand. That is Francesco Ciartino. I believe it should be possible for the audience to speak directly.
So may I ask you if you still see my screen?
Can you hear
Yes.
me?
You do, right?
Yes.
Okay, perfect.
Hi, Vincenzo, can you hear me?
Hi, Francesco, yes.
So, no, beautiful presentation as usual. Just a curiosity. So you showed that this nice idea of merging the energy coming from above and energy coming from below. Yeah. And you showed that this works. Is this connected to the fact that the two power laws have a different power?
Yeah, absolutely. That's precisely it. And so let me. I was a bit quick, perhaps, at the end. So so first of all, let's review what we call left and right. So this is the picture, Francesco, right? Below this Kc, that's to say for wave for K less than Kc, there is the 3D cascade, because the odd viscosity term that has Laplacian dies. Okay. Now in this regime is Kolmogorov scaling. So this power law is K to the minus 5/3. Well, and that was known, of course. What we had to figure out is what happened above Kc, where the odd viscosity dominate, because this Laplacian then becomes strong. We're going to have an inverse cascade that we know from qualitative arguments, like the comparison to the rotating case, or something called Taylor-Proudman argument, if you want to be more specific. But when you do that trick of putting the Kreisman formula, the spectrum of the waves of odd viscosity, notice what you see here, you find here, Francesco, is a spectrum that doesn't go like K to the minus 5/3. It goes to K to the minus 1. Okay? And in addition to that, also has a prefactor that depends on odd viscosity. So what you do is you take this and you match with that. Since they have different scaling with K, you can then characteristically find the Kc that depends on odd viscosity, and that's how you get the match.
If you would have imagined a different method, so not the odd viscosity, something else, I mean, yes, that would have by chance created the same power as Kolmogorov, this would not be possible.
Yes, absolutely.
Okay.
Absolutely.
Thanks.
And conversely, if you don't do odd viscosity, but maybe some other chiral mechanism or some other things that that gives you a power spectrum of, say, wave turbulence with this characteristic, with the formula. There's not k2-1, but something else that is whatever you want, that is characteristic of that process, you could do the same trick. And that's exactly what this slide that I flashed at the very end real fast is. Depending on what you have on the left and the right, you could have odd waves, Rossby waves, or other things, and you will have a scale that you single out by matching those two spectra that will depend on the characteristic of those two problems. But you could still have that pattern formation mechanism that I described also in those cases. Okay, that is the sort of most general way of looking at this.
I don't see currently any hands, but in the meantime, I guess I have a question. And the question is that at the very beginning of your talk, you also mentioned, and you said, okay, this can inspire also new experiment. And of course, you showed a lot of different, like very, very different experimental systems with this odd viscosity. Which do you think is what do you think is the most promising direction to go in order to see clearly this pattern formation in the system?
So there's two things that one can do. One is take the mechanism of pattern formation that we're considering, this matching of the two cascades, and not even look at all viscous fluid, but some of the other candidates on the final slide. In that case, I would not even be surprised if you find the experiment being performed in nature. However, I'm going to take your question to be a bit more specific and to mean, let's say that we want to do it without viscosity. After all, 3/4 of this talk was about that. How would we go about doing that? Well, and one modification of the current experimental platform where odd viscosity has been measured are needed. So there are two things that are important, three things that are important. First, you might have noticed that this system had 3 dimensions. Okay, so if I go back here to this sort of array of efforts that have been done in the recent years, the only one where odd viscosity has been measured in a 3D system is the polyatomic gases. So if you want to do it in a say classical system, you got to make a fluid with odd viscosity in 3D. To the best of my knowledge, no such thing has been reported yet in soft systems of the type of spinning embryos or spinning colloids. Nonetheless, if you take say an object, if you take an object with a magnetic dipole, you can spin it in 3D around the fixed axis. There's no reason or principle why this should not be possible. It's just you would have to do it also in a regime that is inertial. Okay. Now notice that some of the things here, especially on the right-hand side, the polyatomic gas or the graphene, you could more easily go there. But at least the one on the left, the spinning embryos and the spinning colloids, they have underdamped dynamics. Why? Because the colloid is the size of a micron. Now, once again, there's no reason why you have to do the colloids. If you have a big enough tank, you could have an object that's more like a grain. It could be in the inertial regime. And then you can go to high Reynolds number. Because if you are overdamped, it's hard to go to high Reynolds number. To best of my knowledge, that's not been done. And final, the thing that you need to do is you have to spin them with various degree of speed of spinning, because you want to see the dependence on the odd viscosity, and the odd viscosity will depend on how fast you spin. So in principle, there's no constraint on how fast to spin, and the odd viscosity divided by the normal viscosity scales linearly with the degree of spinning. But in different platforms, there may be practical reason why you can't spin faster than something. And you have to somehow overcome them so that you can go to a regime where odd viscosity can be dominant even over normal viscosity. These 3 challenges, while in practice not, I don't see a reason why one couldn't do that, they've not been simultaneously solved in a single experimental platform. As you can do, the polyatomic gases can do 3D, but we haven't, to the best of my knowledge, none have been studied in the turbulent regime.
There is maybe time for a very, very quick question. We have less than 1 minute time. In the meantime, I have to advertise the next talk in case someone else has a question. I am afraid I cannot actually share my screen at the moment. Vincenzo, could you stop sharing your screen for 1 second so that I can put up the next slide, and then I will remove it if there are more questions.
Go ahead.
So in the meantime, I advertise the next talk on January 31st with Ask Me Anything between Roberto Piazza and Francesco Sciortino, and the seminar by Stefano Sacanno. And now I think if there are no more questions, then I would like to thank very much all the participants, Roberto and Cristina and Vincenzo, for the, again, wonderful soft discussion, and I'll see you next time.
Thank you.
Thank you. Bye.
Thank you. Bye.